do the net force is defined as a summation. That is, when you have vectors here, it really is only plus signs because that is a sigma for sum. It's not a difference. The differences show up because, like in the earlier example, I chose up to be the positive direction. So these in one dimension would have, or these would have negative components compared to that one, is a way to say that. Okay, so Newton's second law says the net force on the table is the mass of the table times the acceleration of the table. The acceleration of the table is 3 meters per second squared. Oops, I forgot. It is upwards. The mass of the table is 20 kilograms. So I've got all this stuff. Okay, so this is equal to the sum of those three terms. So I'm going to show you something interesting. I know how to calculate this, and I know how to calculate this. And what that means is that this and this are knowns. So I'm going to put them on one side. But these two things, they're not knowns yet. I don't know their value. In fact, actually, do you remember this is actually our original problem, which was the original reason why we started any of this analysis with Newton's second law. So the point is, I don't know this. This is actually the goal of my problem. This is a, oops, sorry, I've been pointing the wrong thing. This is the goal of my problem. This is something I actually also don't know. Let me show you what I do know, though. From the previous problem, this is the thing that I do know. I know that the normal force on the box by the table is this value. And this value that shows up in this next piece of the problem, can you see the difference? The box, on the box by the table, this is on the table by the box. So the table and the box are in opposite positions in these two situations. This I'm going to come back to in just a second. All right, so remember I told you that I was going to move all the unknowns to one side. So I'll put unknowns. I'll put them on the left, and I'll put the knowns on the right-hand side. So the knowns side is the mass of the table times the acceleration of the table. And then this is also a known, but I'm going to subtract it to the other side. So there is an algebraic minus sign that just showed up. So this is the weight force acting on the table. The unknowns are left over, so I'll leave them over with the plus signs. I didn't move them, they just stayed there, so they just keep the same sign as they had before. So I've got the normal force on the table by the elevator. This is the goal of my problem, plus the normal force on the table by the box. Okay, so I got knowns. I can calculate easily the weight of the table. Here it is. I can calculate easily the mass of the table times the acceleration of the table, excuse me. Here's the acceleration of the table, mass of the table. I want to know this. This is the goal of my problem. What is the net normal force on the table by the elevator? So problem is, I've got two unknowns and only one equation, and you know from your algebra class that that doesn't lead anywhere. Well, it does lead somewhere, but it's not going to lead all the way to giving a vector value for this. So let me go back and talk about this. So I want to remind you that Newton's third law, one way to say what Newton's third law is that in any interaction, in any single interaction between two objects, let's call them 1 and 2. Newton's third law is stated this way: the force on 1 by 2 is equal to but opposite the force on 2 by 1. if this is the action is equal to the opposite of the reaction in any particular interaction. This is an interaction between the box and the table. This is an interaction between the box and the table, but in the reverse. So if this is the action, this is actually the reaction right here. So by Newton's third law, and because we solved this earlier problem, the normal force right here on the table by the box is equal to the opposite of the normal force on the box by the table. So we can use Newton's third law to know this unknown thing right here. So this is not unknown if we remember how Newton's third law works. So what this means is so the normal force on the table by the box is the negative of the normal force on the box by the table, and the normal force on the box by the table is 128 newtons upwards, like this. So negative upwards is 128 newtons downwards. So I'm going to use this as 128 newtons downwards. So this is the normal force on the table by the box. Here it is. This is the arrow representing the normal force by the table on the box. Sorry, I just said that. It's on the table by the box. Yeah, on the table by the box. It is downwards, and that was the direction we guessed it was going to be in. So actually, this can also go to the knowns side. So I'm going to subtract it from both sides. So this is the normal force on the table by the box. And so since I've subtracted it, it's no longer on the left-hand side, and I have now a way to finish my little problem. So the only thing left for you to do, let me remind you of what we're doing here, is we want to find, so I just showed you how to find the normal force on the box by the table. Here it is, 128 newtons upwards. And then I just led you through all of the parts except for doing the math to get the normal force on the table by, yes, normal force on the table by the elevator. Yeah, that is what I'm showing you. So, normal force on the table by the elevator. This is the question. Here it is. It's equal to known, known, and known. Once again, you have to be super careful. There are some minus signs that are explicit, but if you were to again choose up is positive, which you don't have to, you could choose the opposite if you want. But if you did choose this, you'll notice that the number that you have to put in for the weight force of the table, on the table, is another negative number. So it's going to go minus, minus. And then again, the normal force on the table by the box pushes down on the table. So this is minus a down, which is an overall up. Yeah. So you're going to accumulate up a big answer, and I'll let you finish this. Okay, so the last problem in this example is to figure out how hard does the rope pull up on the elevator. So here's the rope pulling up on the elevator. And let me give you some notes about that, and let's think about it a little bit. So, question is, here's the rope, the table, and the little box on the inside, and we want to know what is the normal force on the elevator, or the pulling force on the elevator by the rope. So this is really interesting. So if you wanted to do this, you could go and draw the Freebody force diagram for the elevator. So on the elevator, there's actually a couple of forces, right? So the elevator is directly in contact with the table. So this is the normal force on the elevator by the table. the elevator also has a weight, right? That's the weight force on the elevator. And then there is the normal force upwards on the elevator by the rope. And this is your goal right here. So in order to solve this problem, right, this is a known. This actually is, strictly speaking, an unknown, and so is this. But this thing right here, you can use the third law again. And you'll be able to directly, so then you have an unknown and two knowns. Use Newton's second law, you'll have an equation with only one unknown, and you can solve for that one unknown, and when you do that, you'll have answered the problem. But